So this video addresses the relationship between the strength and the cross-sectional area of any symmetric object, such as a cylinder, is one example, or an extended rectangle, which is also called a rectangular prism, where the cross-sectional area doesn't change along the length of the object. So basically what you need to remember when we're talking about this is that the strength is proportional, we use this symbol for proportionality, to the cross-sectional area, which I'll abbreviate CSA. So what that means is that if the strength doubles, then the cross-sectional area doubles. If the strength triples, then the cross-sectional area also will have to triple, assuming nothing else changes. If the cross-sectional area decreases by a factor of 2, so will the strength. So that's what's meant by proportionality. So with that in mind, let's consider what happens to an object. Let's say you're trying to support a very heavy object, and you're able to just do it with a little pole like that has a certain cross-sectional area and therefore a certain strength. It's just able to support that heavy object. And we can say that this heavy object has a mass of, let's just say a mass of 10 kilograms. Some of you may say that that's heavy, others of you may not. But let's say it has a mass of 10 kilograms, which means it's pretty heavy. And so what we're interested in then is the cross-sectional area of the part of the object right here, for instance. How wide is that? Now let's say that we make the mass, and let's say that the initial diameter of this object here is 1 centimeter. So we're just going to say that a 1 centimeter object can just support this 10 kilogram mass. And we'll just, for the sake of argument, say that this is cylindrical in shape, this object right here. Now let's increase the mass by, let's just say the mass is 5 times greater. So I will create a new slide now. Is 1 centimeter, and I'll make a bigger mass. Do it in black. Call this the heavier mass. $50 kilograms. So it's going to need to be supported by a wider object. So the question now is, how much wider is this object here? Does it have to be? That's what we're asking. We can't immediately say how much wider it has to be, but we can say how much bigger the cross-sectional area has to be. So if the mass is 5 times greater, I'll say that, go to black here. I'll say that the mass is 5 times the original mass. So that means that the cross-sectional area has to be equal to 5 times the old cross-sectional area. Alright? So, how much wider does the new cross-section is the new diameter compared to the old diameter? Well, let's find it in terms of radius. So the new cross-sectional area is pi times the new radius squared. That's got to be equal to 5 times pi times the old radius squared. So how does the new radius compare to the old radius? Well, we can cancel the pi on either side of the equation. And we can say that r squared, rather do it in black, r squared, r2 squared, is equal to 5 r1 squared. So let's take the square root of each side, go to a new slide, and we find that r2 is equal to the square root of 5 times r1. So this relationship is what we found out based upon the fact that we know that the cross-sectional area has to be 5 times greater. And you can multiply both sides by 2, so I can do that now. I can say, okay, 2 times r2 is equal to 2. Actually, I'll put it like this. It's equal to square root of 5 times 2r1. I just put this other 2 in here, right there, rather than way out in front of the 5. So, and 2r2 is equal to the diameter. So diameter 2 is now equal to square root of 5 times diameter 1. So this is my result. So my old diameter, going back a few slides here, is the square root of 5 times 1 centimeter, which is equal to square root of 5 centimeters. And square root of 5 is about 2.23 or something like that. So it's equal to the square root of 5 centimeters. You can calculate what that's going to be. But that's how you figure out what the diameter is going to be as a result of the change in strength required of a pillar of some sort. Okay.